I am back with the damped harmonic oscillator. Maybe you're tired of the damped harmonic oscillator. Maybe it's dampening your spirits. I get that. But I want to do some more. And so what I want to do is to continue my creation of a phase space plot for a damped harmonic oscillator. And what I want to do is to plot a phase space as the parameter beta increases, so you get more and more drag. So kind of see what happens as you go along that way. So just as a reminder about phase space is plotting x on the horizontal axis and x dot, the velocity, on the vertical axis. So if it's just not, and I'll start off with no dampening, it'll just be a circular-ish orbit. And then as dampening occurs, it'll start spiraling in, and then I can increase that dampening constant, and that's going to be great. So what about the damped harmonic oscillator? Well, here I have a mass on a spring. There is a restoring force, negative kx, where k is a spring constant, and a drag force, negative bx dot. So in physics, because we think we're cool, we like to say the derivative of velocity is x dot. Or the derivative of position. So dot means a derivative with respect to time. Double dot means a second derivative. So I have a video on this. I'm not going to go over it because I have a lot of other stuff to do. You get to this differential equation, x double dot, the second derivative of x, plus 2 beta, where beta is a parameter. The drag coefficient is b, right? But this is beta, so there's a difference there. And there's a 2 there because of reasons. The answer is quadratic equation reasons. X dot plus omega naught squared, and again, omega naught is related to the spring constant k. So when you set this up as Newton's second law, you divide it by the mass and you get all these terms. So omega naught is square root of k over m. That was true for the non-damped motion, and then beta is b over 2m. Okay, so I actually have 2 solutions. I'm going to skip the middle solution because I think I don't have to do it. So the first case is underdamped. In the underdamped case, beta is less than omega naught, and when you find a differential equation for this, you get an exponential with the square root of beta squared minus omega naught squared, which would be imaginary. So once you get imaginary exponents, you can convert that into sines and cosines, and I did this twice. So this turns out to be the best way to do it. So the x as a function of time is this exponential e to the negative beta t, so a decaying term, and then an oscillating term, a cosine omega 1t plus some phase shift phi. And you have to have that in there as far as I understand, okay? Because if you want the initial conditions to be constant, then you're going to need a phase shift. It's not as simple as non-damped harmonic motion. Trust me, I tried. So in this expression, I wrote omega 1 is this omega naught squared minus beta squared, because you want to make that term you want to bring imaginary number out of that. So that's how you got that. So that's omega 1. It's not the same thing. So I want to plot this as a function of time, and then I want to look at the case of overdamped. Overdamped is when beta is greater than omega, so you do not get an exponent. You get a term over here that has a beta squared minus omega naught squared, which is positive. And so you do not get imaginary terms in here, so it's not oscillating. So you get an exponentially decaying term, an exponentially growing term, and another exponentially decaying term, and then you have constant C1 and C2. So, but here's the thing, right? I want to change the parameter beta. I want to go from beta 0 to beta is omega naught, and I'll be underdamped. And then I want to go from beta is greater than omega naught. And I had trouble with critically damped and may have been a mind blank. I don't know what happened, but the key is I want to have all my things start with the same initial conditions. So I want to have it start at t equals 0. I want x of 0 to be x naught, some initial position, and I want the initial velocity x dot of 0 to be 0. So there's actually 2 things I need to do. And I'm going to start with the underdamped, and we're going to make that work, and then I'm going to come back and do overdamped. The first thing I need to do is find the velocity. I need to plot the velocity as a function of time, and then I need to find the parameters a and phi that correspond with initial velocity of 0 and initial position of x0. Let's get into that. So I'm going to start right here. I'm going to take this. I'm going to take the derivative, and then I'm going to find my a and phi. Okay. So let's write out that function again, just so we can be clear. We do have a little bit of work to do. It's fine. Work is good. Okay, so x as a function of t is going to be e to the negative beta t times a cosine omega 1t plus phi. And so phi is the phase, a is some parameter. Not necessarily, don't say, oh, that's the amplitude. No, it's not. Okay, it's not, because of the phi. Okay, let's take the derivative. So x dot as a function of t, I'm going to have to take the derivative of this times that plus the derivative of this times that. So the derivative of this is just going to be equal to negative beta e to the negative beta t, because it's an exponential. So I have to take the derivative of the top and I get negative beta. And then I have this a cosine omega 1t plus phi. And remember, omega 1 is not the omega 0. It's different, right? Okay, now I have to add in the derivative of this. So if I take the derivative of this whole thing, I'm going to get negative a omega 1 sine omega 1t. So I'm going to get another negative a omega 1, and then I'm going to put the exponential e to the negative beta t. I'm doing it out of order, and then I'm going to put sine omega 1 t plus phi. Okay, so that's my derivative. It's got two terms. Okay, now let's apply the initial conditions. So I'm going to say x of 0 equals x0. So if I put in up here t equals 0, I get e to the 0, which is 1. And then I get a, so I get a times cosine of 0 plus phi. So it's just going to be cosine of phi. And I don't know a and I don't know phi, so I'm kind of stuck right there. But I can go over here to x dot. X dot at 0 is going to be equal to, let's put in 0, I'll get negative beta. And then that's going to be 1. And then this is going to be times a cosine of 0 plus phi, so just phi. Is that okay if I do that? That's okay. And then I get over here minus a omega 1, that's an omega, and that's going to be 0. And this is going to be sine of 0 plus phi, so it's going to be sine of phi. And that I want to be equal to 0. Okay, so we have to do some stuff here. Let's go ahead and solve this for cosine phi. Right, because I have two equations to notes. Let's solve this for cosine phi. So first of all, I can divide by a, and that goes away. So then I get, I'm going to say beta cosine phi, and I'm going to move that to the other side, is equal to negative omega 1 sine phi. Is that right? If I move that, yeah. And then I'm going to divide both sides by beta, and I get cosine phi equals negative omega 1 over beta sine phi. Now, up here, I know that cosine phi, up here I can say cosine phi is equal to x. Is that what I want? No. I want to say a equals x0 over cosine phi. So this, what am I doing? Let's see. So x0 is equal to cos a0 over cosine phi. What did I do then? Oh, so I also know cosine phi is this. So I can say this is also equal to x0. I think this is a dumb way to do it, but I did it anyway. Divided by all this. So negative omega 1 over beta sine phi. So now I have an equation right here that just deals with, oh, I could have done that over here. Ha, I didn't need to do that. Okay, so let's just take this, and actually I'm gonna solve for sine over cosine. Why did I do that? That was dumb. Ignore that part. I didn't do that. Okay, so let's take this as sine of phi divided by cosine of phi is going to be equal to negative beta over omega 1. If I just solve that for sine over cosine. Is that right? That is right. Yes. And that's going to be equal to tangent of phi. Sine over cosine is tangent. So phi is going to be the inverse tangent of negative beta over omega 1. So I have phi. Now I can go up here and calculate A. So A is going to be equal to x0 over cosine of phi. So you got to calculate the phi first and then calculate A. How's that look? Okay. So let's jump over. We're going to make a phase space plot. I'm going to put in a value for beta. I'm going to calculate my A and my phi. I'm going to plot it. And then what I want to do is animate the trajectory. Okay, so I'm actually going to do two things. So let's just start to make sure it works correctly. Jumping over to Python. Hello, Python. Okay, so I've already got this started. I put some stuff in here just because I didn't want to, I knew this would be long anyway. So I have here a graph. I put in x max and x min because I already knew beforehand. If you're fine with that. I think you should be fine with that, right? That just sets the spaces so that it doesn't zoom in and zoom out, which you don't have to put in there. I'm just trying to make it look nice. So I have my t, I have my dt, the mass, my b, which I don't actually need because I'm actually changing beta, not b, and I'm not changing k. I'm changing just beta. So k, x naught, and then x equals x naught. I don't need that right there. Okay. So the first thing I'm going to do is to calculate my values. I need, let's just set beta equals to 0. See, so normally I should calculate what that was, but I wanted to set it equal to 0. I need, what else do I need? I need omega naught. I do need that. Okay, so omega naught, omega 0 is equal to the square root of k over m. And that's going to put my maximum value for beta, right? Because once beta gets as large as that, then I don't have underdamped. I'm going to need this omega 1, which is the square root of, what did I call it? Omega 0 squared minus beta squared. And yes, I'm using b for beta, even though I shouldn't do that. I did. Okay. So now I need to calculate my parameter phi and a. So I'm going to say phi is equal to, what did I say? Inverse tangent a. Now, this is GlowScript Web v Python. It has built-in trig functions. If you're doing this in plain Python, you'd have to import numpy, numpy. You call it what you want. I like saying numpy. It just sounds fun. Inverse tangent, negative b divided by omega 1. And then I can calculate a equals, what did I say? x0 divided by cosine of phi. Okay. So now let's run this thing. So I have my a, I have my phi. I can calculate x. I can calculate x, the derivative of x. So up here, I'm going to say while t is less than 3. I just pick a value. Rate 100. So rate tells it to do no more than 100 calculations, no more than 100 loops a second. Since I have a time step of 0.01, this will make it run in real time. It should take 3 seconds to run. Up here, my function, I skipped over this. Here's G1. Let's go over all the things. Title, that's just space. That gives a space in the top, makes it look a little bit better. X title is X, V title is V. The width and the height, I put at 400. I want it to be square. You can change those. X max is the maximum X value, and X min and Y max, Y min. This F1 is my function that I'm plotting, and dot is true, so that when it draws it, it'll leave a dot right there, and that's kind of cool. Okay, so I want to calculate X. So X is going to be e to the negative bt. So exponent is e to the times a times cosine omega 1 times t plus phi. Is that right? That's what I had. Yep. Okay, now I need to calculate the velocity. I'm going to call it x dot. X dot equals, I'm looking at my equation here, negative b times exponent negative b times t times a times cosine omega 1 times t plus phi. And then I'm going to have minus a times omega 1 times exponent e to the negative b times t, not 6, times sine omega 1 times t plus phi. And you know, in this case, I put the A1 at the front just because I want to be different. Okay, so I have x and x dot. Now I can plot them. F1 dot plot is going to be x dot. And now I need to increase time. T equals t plus dt. Now remember, I put beta is equal to 0, so it should just be an orbit. Let's see if that does indeed work. It's best to start off with simple cases. Okay, so everything looks good so far. Let's see if it makes a complete orbit. Okay, that looks good, right? I think we can save this. Let's call this changing drag phase space simple harmonic oscillator. Yeah, that looks good. Okay, so now let's just increase beta. I want to make sure I don't increase it greater than omega. So maybe I should print out omega right here. Print omega 0 equals omega 0. Because if it's greater than that, then things are not going to work. And I'm sure it's going to be fine. Okay, so 3.16. Okay, so I want it smaller. Let's just make something small like beta equals 0.3. It's smaller than that. Now, in this case, I should see a decay. Now, notice that it's two important things. Let me run this. There's two important things that I like here. One is it orbits clockwise, right? Because right here, I have a positive position. And that means that and of zero velocity. It starts at zero velocity because it's on the v equals 0 axis. That means that it should start moving backwards and have a negative velocity. So that's the way it should go. And also this does spiral down. So there's two things. I want to orbit the right way, and I want to start with a 0 velocity. I want to start with x equals x0, v equals 0. That looks like it works. Okay, so I'm pretty happy. Now, let's animate this. I want to see what that trajectory looks like as I increase my value of beta up to omega. So I'm not gonna draw the trace. I'm just gonna start with it right there. And another thing too, I'm actually gonna need it to. I want to go all the way down here to the end. So let's say, let's just say 10. Let's see if it does it close. It won't get all the way there, and I'll make it run faster. Let's just see if that does it. Yeah, that's what I want. It's not all the way there, but that's close. And now we can see the change in that shape as I increase the drag, and it's going to be great. Okay, so to do that, I actually need to use a different method for making an animated graph. And so what I want to do is to do this. Let's say, let's go up here, f data equals an empty list. And you can call it whatever you want. I'm calling it f data. Now, instead of plotting down here, let's just delete that. Instead of f1.plot adds a data point of x dot to my graph. It adds one single data point. So as I go through the loop, I add a whole bunch of data points. Instead of doing that, I'm going to add each data point to a list. So let's say f data equals f data. And if you did append, that's fine. I don't like that. X dot. So this is a data point. It's a list in a list of x and x dot. So I'm going to have a whole bunch of pairs, and I'm going to have all my data. At the end, I can then plot all that data at one fell swoop. So if I say f1.data equals f data, then it will just plot the whole thing. So let's see if that works. I'm going to turn off the dot because I don't want it. I don't need the dot is there anymore. False. So let's run that. And it didn't do it. Oh, there it did. Okay. Oh, I had that rate statement in there still. I don't need that rate statement. So that looks good. Okay. So now let's go back up here to beta equals 0. And now I want d beta. Because what I'm going to do is to make a trajectory, plot it, increase my beta, plot it, increase my beta. And so I can animate how this goes over time. So let's say beta is, let's say d beta is 0.1. We can always change that. And I don't want this. I want that to go as fast as possible. And so what I want to do is to say while beta is less than omega 0. I do not want to do beta is equal to omega 0 because that's a different equation. Now here I do want to do a rate. So let's see, 0.1, if I do rate of 100 and it's 3 seconds, I think, let's try that. Rate 100, we can always change that. And so then I'm saying I'm going to do a loop inside of a loop. So I want to, inside that loop, I want to do all this stuff. All that stuff. So I can indent that. So I'm going to, I need to first reset time, t equals 0. I need to recalculate a and phi, right? I need to recalculate all this stuff. Because as beta changes, omega 1 changes. Omega 0 is not going to change. But I need to recalculate all that stuff. I need to recalculate phi. I need to recalculate a. Because they both depend on, in a sense, they depend on beta. It's right there in there. I need to empty my list. Set time is equal to 0. I think that's good. And then do my loop, plot it. And then after I plot it, I'm going to increase beta. Beta equals beta plus d beta. I feel like I'm missing a step. Reset the time, recalculate my parameters. Maybe it'll work. I don't know. Okay, so let's see if this works. Yeah, that worked. Okay, it went a little fast. Let's make it a little bit slower. So let's say rate of 50. Well, I could leave it like this. I could do dB of 0.5 just to make it. So you can see the trajectory as, let's just make that even slower. As the parameter increases, then the drag increases, it stops oscillating, and eventually gets down to this point where it's essentially not oscillating. But and every time, notice what's really important at every time. It starts at the same position in phase space, because that means it starts with a position of x equals x0 and a velocity of 0. It starts in the same position, and it goes that way. So I think that's pretty good. Now let's just jump to the case. I'm going to skip the case. I think it'll be okay. I skip the case of omega, of beta equals omega. I'm going to go into beta greater than omega, but I have a different equation, so I need to calculate different parameters. So let's go back over here to the paper view. Okay. So I plotted this, right? I plotted this, and I calculated a and phi so that would work. And you know, that is confusing, that this, even if you start at a velocity of 0, then this phi is not always 0 because of that term right there. I hope you see that. Okay, now let's go over to this equation. Now this is the same, it's really the same thing, except that I have new omegas up here, and they're not imaginary. Because if beta is greater than omega 0, that's going to be a real number. So this is just an exponential thing. So what I need to do, though, is to calculate C1 and C2. Okay, so let's do the exact same thing. The first thing I'm going to do is to take the derivative of this, and then I can use that to set my parameters. So here I have, let's just go ahead and write up here, x, that looks weird, x of t, exponential negative beta t, C1 e to the omega 2t plus C2 e to the negative omega 2t, where omega 2 is the square root of beta squared minus omega 0 squared. It's just a value. Okay. But you see, I have to have beta greater than omega 0. I have to. Okay. Let's take the derivative. So x dot of t, I'm going to take the derivative of this, negative beta e to the negative beta t times C1 e to the omega 2t plus C2 e to the negative omega 2t. Now I've taken the derivative of the inside stuff, so I'm going to say plus e to the negative beta t times the derivative of all of this is going to be C1 omega 2 e to the omega 2t minus C2 omega 2 e to the minus omega 2t. Okay, so I'm gonna need this to plot. But now I need to find C1 and C2, and I can do that with my initial condition. So right up here, I'm gonna say x of 0 is gonna be equal to x0. So if I put in 0 up here, I get e to the 0 is 1, e to the 0 is 1, e to the 0 is 1. So I get C1 plus C2. Okay, but I don't know C1 and I don't know C2. Okay, now let's do, let's see, check my notes, because I know I made a mistake here before. Okay, so now let's do x dot of 0. If I put in 0, I get negative beta. And then I have this term, which is 1. And then I have this term is going to be C1 times 1 plus C2 times 1. Now I have this term as 1, but then I have plus omega 2 C1 minus omega 2 C2. And I want that to be equal to 0. Okay, so let's see what I did. Okay, so let's just get my C1s and C2s together. So if I rewrite this equation, that one's easy. If I rewrite my equation up here, I can write this as C1 times, I have a negative beta, and I have omega 2. Omega 2 minus beta. And then here I have plus C2, I have a negative beta and a negative omega 2. Negative beta minus omega 2. And so if I add these two together, that has beta equal to 0. So I can solve, what did I do? All right, okay. So let's solve this for C1. So if I solve this for C1, I get C1 omega 2 minus beta equals negative C2, negative C2, negative beta minus omega 2, which is equal to C2 times beta plus omega 2, right? Because I bring the thing in. Now I divide both sides by this, and I get C1 equals C2 beta plus omega 2 over omega 2 minus beta. Now I can plug this in up here. And so if I plug in C1 as this, then I get x0. I have a C, these are both going to have C2. So I'm going to say is equal to C2 times 1 plus this. Yeah, 1 plus beta plus omega 2 over omega 2 minus beta. So C2 is going to be equal to x0 divided by 1 plus beta plus omega 2 divided by omega 2 minus beta. And then C1 is going to be x0 minus C2. Okay, so let's jump. I should try this as a phase space, but I'm not going to. I'm just gonna jump into it and see if it actually works. So remember omega. So let's set up here. Oh, I got to go back over here. I was jumping ahead of you. Okay, so down here, I'm going to repeat this whole thing. So I'm going to go down here, and I'm going to repeat it. But now I want to do this for while beta. So I'm going to set beta. Beta equals omega 0 times 1.001. So it's greater than omega. I skipped over that part where it was not. And I don't know if this is okay. It may not work. And now I want to run this while beta is less than, let's say, I don't know, 1.5 times omega naught. I mean, who really cares? It's not going to be that cool. So then I have the same t. Omega 1, I do not need. I need to calculate omega 2, right? So omega 2 is this backwards. Did I call it omega 2? Yeah, I did. So beta squared minus omega naught. I don't need this phi. I don't need that. Instead, I'm going to calculate C1, C2. C2 is equal to x0 divided by 1 plus beta plus omega 2 divided by omega 2 minus beta. Is that right? Yep. And then, oh, that's C1 too. That's C2. C1 is x0 minus C2. Okay, so now I have C1 and C2. Now down here, I'm going to have a different x. Let's get rid of this. So x, I'm just looking at my equation right here. Exponent negative beta times t times C1 times exponent of omega 2 times t plus C2 times exponent negative omega 2 times t. And then x dot is not this. It is negative beta times exponent negative beta times t times C1 times exponent omega 2 times, if I don't make an error in here, this is going to be amazing. C2 times, same thing, exponent negative omega 2 times t. And then I have plus exponent negative beta times t times C1 times omega 2 times exponent omega 2 times t minus C2 times omega 2 times exponent omega 2 times t. Maybe that's right. So then I plot that, increase beta. Okay, I don't know, man. Let's just try it out. I mean, you're just going to have to take a chance sometime. Okay, there's a little bitty jump in there. I don't know if you noticed that, and then where it skipped over the value where I didn't want to do critical dampening. In critical dampening, omega is equal to beta, and I have a C1 plus C2, and I don't really know how to find those because I got like C1 plus C2 is equal to X0, and C1 plus C2 equals 0, something like that. And I just didn't want to deal with that. So, but I'm pretty happy with the way this is. Oh, you can't even see the whole thing, but there you go. So that's looking at the phase plot of a damped harmonic oscillator as beta increases from 0 to 1.5 omega naught. I'm pretty happy with the results. It is surprising how difficult it is to find those initial conditions. I did this before and I made a mistake because I assumed bad things. I assumed I was dealing with just a simple harmonic oscillator, and damped oscillator is not a simple harmonic oscillator, and that's what you should learn from this whole thing. The playlist for this whole thing would be down below. I can give you the code for this down below too. If you have any questions, let me know. So my oscillation playlist, all my oscillation stuff in here. So hopefully you find that useful. Later.